Hey guys, just connecting to the internet. So I have a Mac with one of those fancy ports, so you got to use these like 900 connector things. But I find that connecting to the actual internet. Hi Sky. Oh, good. I forgot to bring a periodic table, so I'm going to pull one up real fast. You were periodic. This is exciting. I've always really enjoyed that you guys are going to get to watch this. I wonder where I would have hidden that. Sky, there are office hours on Friday. They're from 10 to 12, and they are on Zoom. So if you don't know how to get to those, you can go to the Canvas homepage, which I'm going to verify that this is exactly where I think it is. If you scroll down, I don't know, there's like the Flasky picture and then some stuff about me. There's a link that says Zoom. If you click that link, it will take you to the stuff. Good. I'm still downloading a periodic table. Mostly because I forgot one in my office and I don't want to run across the building to go pick one up, which in hindsight would have been a much better move than this. This is dumb. There it is. Download. Pull this back up. Whoa. Crashing my. Yeah, I'm riding the struggle bus today. Perfect. And so Sky's asking about the worksheets. On Canvas, if you need the worksheets, you can find that information, or the keys will be posted on this weekend. Probably before Monday, so that if you guys study over the weekend, you can look at them before class on Wednesday or before the exam session. Jordan asked, can we discuss the different equations and what they're used for? I have several examples. Do you have a specific equation that you're curious about, Jordan? If you do, I am happy to answer that. There haven't been any other questions thus far. Other things I think we want to know. So next week is, I have no ideas on the dates because dates don't matter anymore. On Monday, we will do the exam 2 review, which those questions will go up on Canvas probably on Friday, but definitely before Monday. So those will go up, and then on Monday, I will solve those and answer any questions. So if you have a question about any material, you can ask me about it then. And then so that's on Monday, and on Wednesday, so 1 week from today, will be exam 2. It is not the exact same, because obviously it's new material, but the format will be the same with the 1 question at a time and everything else on Canvas, 75 minutes. I will fix the timing issue. Like, I've done a lot of research. I've had someone else look at it and make sure I'm not going to screw it up again. It should all work. You should see the correct time when you start. So could y'all ask for the quantum numbers? So, and David gives the triple caret same. So I think what we'll do is we'll start with quantum numbers. So it's not a different format. We're gonna start with that instead of the first questions on the list. And yes, Jordan, that is correct. On Monday, on YouTube Live, from 3 to 4:15, these are all, I don't want to say optional, strongly recommended, but on Monday from 3 to 4:15, I will answer exam questions, so you should come with those, as well as do a handful of review problems like we did like 100 years ago in September. So let's talk about quantum numbers, because quantum numbers can feel super complicated. So quantum numbers are like an address. When we think about a quantum number, you want to think about it as an address. So I think I have some questions. So let's look at this question over here. So the quantum numbers for an electron in the 5px orbital. So quantum numbers, you can really only ask about 3 things. One is, which of these is an allowed set of quantum numbers? And we'll talk about that last. So which of these is right, which of these is wrong, which would be like a multiple choice question. And I hate multiple choice, so we're not using this. So that's an option. The second option is that you ask, what are the allowed values, or what are the 4 quantum numbers? So the hardest part about quantum numbers is realizing that there are lots of allowed values, but when I ask like this, sorry, it's mirrored, what are the quantum numbers? Your goal is to just tell me what they are. So let's talk about the 5px orbital. So by having a subscript designation, that tells us that we can identify where this electron is. So there are 4 quantum numbers, N, L, M sub L, and M sub S. So N is the principal quantum number. It tells you what is the shell. Basically, if it's provided this, it's asking you what is the big number. So most of the time on my assignments, that's where you'll find it. In Alex, it will ask you some slightly different questions. So we'll talk about that. So N equals 5. L, for this electron, L comes out of, there's a table in the slides where it says, for L, S equals 0. No, yes. S equals 0, P equals 1, D equals 2, F equals 3. In that table, which I do not have a copy of today, that tells you for this electron that L has to equal 1. So N and L are almost always going to be given provided you have this electron, this information. Where it gets more complicated are M sub L and M sub S. So for L equals 1, the allowed values for M sub L are -1, 0, and 1. But I ask you in this question, what are the 4 quantum numbers? In Gen Chem 1, you just pick one of the allowed values. Now, if you love chemistry and are a chemistry major, or I've made the case that you should switch to chemistry, then in later classes, like this course called Physical Chemistry, you will learn that the 5px does in fact correspond to one of these numbers. But this is Gen Chem 1, and that's like not our business. It's outside the scope of this class. So you should pick one. I'm feeling positive today, so I'm going to pick +1. So M sub S has 2 allowed values for every single orbital. It's either +1/2 or -1/2. Now I'm going to put +1/2. You can include a plus sign here, but you don't have to. So when it asks for the 4 quantum numbers, N comes from this number here. The orbital tells you L equals 1. As long as that orbital is defined, px, dxy, dyz, really if there's anything subscripty here, it tells you that it is a real orbital. You don't need to remember what they look like or anything else. But that just tells you that any one of the allowed values. So I rarely am like, just pick one, as long as it's allowed. But the thing is, it can only be 1. You can't write that M sub L equals all of these, because that's not a specific address, okay? It's an address, it can only have 4 numbers. And M sub S is the same. So while I erase this and start working on the 3DXY question, if you guys, for those of you who are like, I got some questions. Can you write in the comment box which of these 4 quantum numbers you're still kind of struggling with? What about these is complicated? And it's okay to write like just 2 more examples. I did not follow that. That's an acceptable option. Okay, so Catherine, I hope this helps. She says she's struggling with all 4, and that helps me. And so Jeremy asked, where do L and M sub L come from? So in the videos, and if you haven't watched the video on quantum numbers, you should definitely watch that. So N is the periodic, it tells you the shell, right? So then L tells you which orbital it is in which shell. So in the S, or in the n equals 1, the only option is S. In the n equals 2, we have S and P. And so that's where the L values come from. The M sub L tell you the orientation of the orbitals. So we know that there are 3 degenerate p orbitals, right? Degenerate means they're all the same energy. So you have the px, the py, and the pz. So those 3 items, we're asking where the electron is in one of those. So let's look at the 3 dxy. So in this case, because it tells us for the orbital, so this right here tells you, I want to know about the electron in that specific place. So in this case, we know that it is the n equals 3 shell. So that tells us that n equals 3. And we know that because the big number is 3. The L comes in the next one. So basically, it's like a shorthand. Some people use their Instagram handles to basically be like, not a code, because that sounds weird, but if your Instagram handle is like Florida _ Jacksonville _ UNF Drive _ Building 50, that's what the, it's kind of like a zip code, but that's what these numbers are. It tells you the state, n equals 3. The city is the L. M sub L is the street, and M sub S is the house number. Together, it tells you where you are, right? So you can only be in one place at a time, unless you have superhero powers, and then we should talk, because like I want to do that too. So for D, we know that in that case, L equals 2, because the L table, so if L equals 0, it's an S orbital. L equals 1 is a p orbital. L equals 2, D. L equals 3 is F. And if you were to have, we believe, based on science, that someday we will find electrons in a G orbital. We haven't yet. So we know that L equals 2. M sub L comes from the L value. L could be any, L is 2. So M sub L could be -2 to +2, counting through 0. Pick any number. Any number. -2, -1, 0, +1, or +2. I'm going to go with -1. So M sub S, every electron can only have 2 options, +1/2 or -1/2. In this case, we're going to use +1/2. So the quantum numbers are just these 4 things. So let's look at the 5fxy. the n equals, big number tells you 5. For the f orbital, s, p, d, f, so that's going to give us 3, L equals 3. M sub L can be anything from negative L to positive L. So in this case, I'm going to choose plus 2. And M sub S equals, now I'm going to pick negative 1/2. There are, as long as you choose any one of the allowed values for M sub L and M sub S, your answer is correct if I ask for the 4, right? So where I have found that students get confused is trying to match the allowed values with the what are the 4 quantum numbers, right? So the reason those are tricky is because what we know is n equals 5 tells us that the allowed values could be 0, 1, 2, 3, and 4. Those are the allowed values. Those don't necessarily tell you where it is. So in the beginning of this conversation, I talked about the other questions you could ask. Like, are these quantum numbers correct? And so that's another way to think about this. So if I gave you these 2 values down here at the bottom, so we can compare all 3 of these. So the other question you could have been asked is, which of these is an incorrect set of quantum numbers? And then you would have to utilize the allowed value rules. So it turns out that the top and the first and the third are correct, but this one, n equals 3, so L is correct because the allowed values are 0, 1, and 2, so we're good. But M sub L cannot equal 3 based on L. So in this case, all of these, those are really the only questions. And so in a second, we'll work, I think, number 5. Is a mediocre question, but we'll look at that one next. So Davis asks, why did we make M sub S plus 1/2? Then he followed that up with, do we just decide if we want it plus or minus, or does it not matter? So you get to decide in this class. Now, in other classes, there are other things. So you can pick plus or minus. There's only one way that you wouldn't, and you might encounter that on ALEX where it says, like, if one electron in the orbital has this configuration, what does the other one have? Because this basically tells you, if you were to think about the 2 electrons in an orbital, basically you can have the mental image that the up one is the plus spin and the minus one, or the down one, is the minus spin. So the only way it matters is if you know what the other one is doing. So in this class, just pick one, but what it is not both. So it's not plus or minus 1/2. It is either plus 1/2 or minus 1/2, not both. So Jordan asks, would L equals 4 be a G orbital? Can you really have an angular momentum number that is greater than 3? Yes, and yes. So just because, so this is where it gets a little murky. We've not seen anything there, but mathematically we know that it exists. So you can solve the wave functions with L equals numbers more than 3. And they will give you real allowed values. So it does happen. We just haven't observed it yet. So that's kind of my thought on that. Jeremy Newman asks, what does the big number in front represent? And David is correct. It is the n. So the quantum numbers, so video 6.3 and 6.4 kind of tie together. So the n tells you which N shell it is, or which row it is on the periodic table. The flip of that is that this basically tells you, so this is N, F is L, these subscript values are M of L. And then you assign a plus or minus M sub S. Other questions about quantum numbers, or we'll start to look at what are the allowed values, and we'll go from there. Yes, N is a row. On the periodic table, N is a row. So you can try to identify electrons based on this, but that is not the most correct way that you can use quantum numbers. So the row, so N equals 5, if you're looking at a periodic table, would be the row with like rubidium, strontium, yttrium, zirconium, those elements in it. Glad to help. Okay, so let's think about some allowed value questions. So, question 5 is garbage, to be honest. It says, what are the allowed L values for electrons that are in the 6d orbital? We're going to just kind of erase this, not erase, but the 6d has an L equals 2, so that's not an allowed value. So let's ask for the allowed L for N equals 5, N equals 3, N equals 1. So the allowed L values are determined by N. So you can either ask what is allowed, or you can ask what are the quantum numbers. Those two pools of information don't live together. They live separately. So for N equals 5, the allowed values would be L equals 0, 1, 2, 3, and 4. So for N equals 3, the allowed values are L equals 0, 1, 2. For N equals 1, L equals 0. So when you look at the periodic table, we know that there's just the 1s orbital. For N equals 2, we know that there's the s and the p orbital. So, but your electron could either be in the s or the p. So that's how quantum numbers tells us about the electrons. So what other questions do you guys have? Do you have more questions? I do want to work some of the math equations because I think it was Jordan, I think so, that asked at the very beginning, can we look over some of the equations? And so I want to make sure we get to that part, but quantum numbers are often pretty tricky. So what other questions do we have about quantum numbers? Did this help? Are we like, I hate quantum numbers, I'm just going to take it, or not? So Jeremy asks, what are the allowed M sub L values for the F orbital? So for the F orbital, we know that the L is L equals 3. So the M sub L values can be -3, -2, -1, 0, 1, 2, 3. So there are 7 allowed values, 7 allowed M sub L values for the L equals 3 orbital. Okay, well, glad I answered that. All right, let me double check. Any other questions? It doesn't look like there are any other quantum number questions. Could y'all, I agree, more practice, and don't forget, I think there's a bunch of these on the, what word am I trying to find in my brain? The chapter 6 worksheets. I think there are several on there, and there will be solutions. So you can do that, and that will be quite helpful. So let's We're going to start with question number 1. And so that question states, what is the frequency in kilohertz, so units matter, in this case, of a laser pointer that emits light at 723 nanometers? Light, in terms of when we talk about like a laser pointer, or lights in your house, or lights on an airplane, or really any visible light, is almost always reported in nanometers. I just didn't do n equals 4. But you should be able to follow the pattern that it would be 0 through 3. So in this equation, we know that frequency and the wavelength of light, so the wavelength is reported in this case as nanometers. So we know that wavelength equals 723 nanometers. And so the equation we want to use is C equals lambda nu. So the speed of light equals the wavelength of light multiplied by the frequency. The speed of light is a standard, so C equals 2.998 times 10 to the 8th meters per second. And we're looking for frequency equals question mark. So we can rearrange this equation to solve for frequency, and that equals the speed of light divided by the wavelength. So if we set that up, it's going to be 2.998 times 10 to the 8th meters per second divided by 723 nanometers. Now, nanometers and meters do not cancel. They are not the same unit. So we need to convert one or the other. I'm going to convert nanometers because it's easier. You will get the same answer if you converted meters into nanometers, though. So in 1 meter, there are 1 times 10 to the 9th nanometers. So that lets these two cancel. My meters both cancel. That gives us the answer in Hertz, which is 4.1466 times 10 to the negative 14 Hertz. So in the question, it asks for your answer in kilohertz. So there are 1,000 Hertz and 1 kilohertz, which gives us, and we need to keep track of our sig figs, which is 4.15 times 10 to the negative 11 kilohertz. I've heard some questions, so I'm coming back. So Jordan asks, can we use the value for C? What value is Alex giving you for C? Because it should be 2.998 times 10 to the 8th. It's supposed to be. So what is that? Can you let me know? Oh, Miss J, I'm glad you figured that out. While Jordan's giving me that value, does anyone have any other questions about this calculation using this equation? Oh, that's a really long number. You should be able to use that number. So the number that Alex provides is a very long number. 299 million, and then some other things. So the biggest downside is that your answer here may no longer be the same. So it is approximately 2.998 times 10 to the 8th. So I will use this value. The biggest issue that you're going to run into is that your number and my number, because we're going to start working with large exponents or really small exponents, that changes the value, or it basically just extrapolates the error. So if you plugged this If you did this question using that number, although I brought a calculator, I can set that up. So 299,792,458 divided by 723 times 1e to the 9. So it turns out in this case, you would have gotten, so using the Alex number, you would have gotten 4.1465. So it's just slightly different than this. It should give you the same number. So if we wanted to convert nanometers to meters, what would the conversion number be, or would it still be 1 times 10? So in this case, although I think that you are correct. Who asked that? Camilla was correct. That should be positive 11. So we fixed that. I don't know why it was negative. I think I just had a moment. So Catherine asked, how did the Hertz turn into second? All right, there's a number of questions. I'm getting a little spaced out. Okay, so Ms. J asks, if you want to convert nanometers to meters, the conversion number be. So 1 meter equals 1 times 10 to the 9 nanometers, or you can use 1 nanometer is equal to 1 times 10 to the negative 9 nanometers. Both of those will give you the same. So why is, you are correct, it should be positive. We'll make it positive here. So Catherine asks, how did seconds turn into hertz? So hertz is the unit 1 over seconds. So Hz equals 1 to the second. You could also see it written as s to the minus 1. Hertz is just that unit. So Carson also asked about 10 to the negative 14. I'm guessing I plugged it in wrong in my calculator or divided by something backwards. So the answer to your question, Carson, is that it should be 10 to the positive 14. And then, let me actually make sure I did that right. 14. Yes, this is the correct answer now that I changed the sign. So what other questions do you have about this calculation? If you have none, hit it in the box. Otherwise, and if you have none, we will move on to number 2, which is on top of number 1. So far, it's not looking like we have any other questions. So, and if you do, we're going to do this kind of math like a lot today. So, in the next question, we want to talk about the energy of a photon of light. So, in my opinion, today, question 1, question 2, pretty simple, just plug and chug. Question 3 and 4 get a little bit more exciting. So, in this case, we're going to start to utilize multiple equations in this type of questions. So, we have a wavelength of light, 562 nanometers, but I want to know the energy of a photon of light. So, we know that the energy of a photon is equal to Planck's constant times the frequency. So you could, using the same equation method that we did on the first one, go ahead and solve for the frequency and then plug it in. My preference, and this is a Dr. Malcolm choice, not a I expect you to make this choice. I only want to use my calculator 1 time. That is my decision. Maybe it comes from the olden days. I don't know. But the reality is, I prefer to manipulate my equation instead of having to do 8 different equations. So I also know that C equals lambda nu. So we can solve for nu and get C over lambda to where I can now plug this value or this in for that, to where the energy of a photon is hc over lambda. So all I did was rearrange the speed of light equation, solve for frequency, and plug that in here. Because now I only have to do one set of math. So when we plug this in, we get 6.626 times 10 to the negative 34th joule seconds, multiplied by 2.998, or whatever that really long number is that Jordan likes, times 10 to the 8th meters per second, divided by our wavelength, which is 562 nanometers. And I have plenty of space. So I'm going to go ahead and convert this to meters. There's 1 times 10 to the 9th nanometers and 1 meter. So if we deal with all our units, our answer will be in joules, which is good because energy should be in joules. So now we can plug this into our calculator. And so in this case, we will get that the energy of a photon is 3.53 times 10 to the, let me make that a little bit easier to read, 3.53 times 10 to the negative 19 joules. So this equation is as simple as number 1 if you do this part. So I will try to post it today. It will be an old. I'm going to try to post the equation sheet today. And so I'll cross our fingers that I can do that during my next class. But if nothing else, it'll go up by Friday, so you can take a peek at it. Feel free to print it out. But I will give you this equation and this equation. You will need to make this equation. Or if you're making your own equation sheet, you can write down any variation of any of these equations. So what questions do we have about this calculation? Or is it as simple as it was on number 1? Let me know. Well, in that case, then I'm on top of my life. Jordan says it's already been posted. That's likely true. I know that the old one is not complete. But if there's already one up there, then I'm not going to worry about it as much today. So Catherine asks, will you be able to use the equation sheet on your exam? Yes, it should be accessible from Respondus, unlike the last one where apparently Respondus had a meltdown. But it should be accessible from there if you need it. Or the other thing I will try to do is to embed it as an image, just like the periodic table. In case the links break, then you can find it in the text at the top. It will tell you which questions or spacer things that information is. So I'll do that. Miss J says she doesn't have any questions, so let's look at number 3. So what is the energy of light, or what is the energy of a photon of light that excites an electron from the n equals 2 to the n equals 7 state, and draw the energy diagram? So in this case, we want to think about what this means. So I'm going to start with, instead of the math, I'm going to start with the drawing of the energy transitions. So when you draw the energy lines, they should basically decay by half as you go up. So you'll notice I used a piece of paper. So we have a big gap, and then they get smaller as they go. They are not equally spaced lines. They're never equally spaced. Pro tip, I'm going to make you draw energy lines on the exam. You will not get full credit if it's a bunch of equally spaced lines. They should decay. You don't need to get out a ruler or a protractor or a slide ruler or anything else to try to make them perfect. Mine are not perfect, but they should look something like this. So we're talking about an energy of light that's going to excite from the n equals 2, 3, 4, 5, 6, 7. We're talking about a way for the electron to go from here to here. So your tail of the arrow starts at n equals 2, and it ends at n equals 7. So the equation we want to use for this is the change in energy between these two states. So delta E equals negative 2.18 times 10 to the negative 18. We forgot our units here. Joules times 1 over nF squared minus 1 over ni squared. So when we plug this into our calculator, it's negative 2.18 times 10 to the negative 18 joules, 1 over 7 squared minus 1 over 2 squared, which gives us 5.0051 times 10 to the negative 19 joules. So Jordan asks, why do they get closer together? So to calculate E, or the energy of any state, it uses the E of any one state, and I think you guys can still see this. So this value is Planck's constant times the speed of light, and I think it's divided by something else. And the Rydberg constant is in there. So if you look in the video, it talks a little bit about how that value came to be. You can plug in all three constants, or you can just use 2.18 times 10 to the negative 18. But for each of these, it's negative 2.18. I'm off screen, hold on. So we'll just write it over there. So the energy of any given state is equal to negative 2.18 times 10 to the negative 18, 1 over n squared. And so as the n value increases, so it'll go from 1 over 1 to negative 2.18, then it will be divided by 4, divided by 9, divided by 16. And so that makes them get smaller in a inverse square component. Does that make sense? So Camilo asks, how do we go about sig figs for these problems since nothing but the n numbers are given? Great question. I have tried on either if on the weekly assignment or it will be on the exam, it will tell you to use 3 sig figs or however many I want. As long as you use more than 1 sig fig, well, really it's 3 or more, I will accept any of those answers if it doesn't tell you how many to use. Because I think a singular sig fig doesn't tell you anything because of how big or small that number is. The energy is negative by convention, I believe. So there's some very complex math that I think I talk about in the video as to why it's negative. But when E equals 0, when there is no energy or the change in energy gets close to 0, the electron is no longer associated with the nucleus. So it's separated. So energy increases from the most negative and going positive. But basically here is E equals 0. And so when the energy is 0, the system is no longer involved. And that's also relative to the electrostatic potential equation of K equals Q1, Q2 divided by D. And that is also coupled in here. So it is negative. other questions, and have I answered any of your other questions that you're running around? Is this making sense? What are our thoughts? And if you are curious, let's go ahead and just make that go away. So if you have no questions and you have not already done this, you can start on this question. Otherwise, in just a second, I will start working on this equation. Oh, Miss J, it's totally okay. The sig figs in this case I just used for, but in anything that is graded, I will accept anything more than 1 if it doesn't tell you, but I will try to use X number of sig figs. And so you'll have to be able to know that. So if this was a exam question, it would say use 3SF. So Jordan asks, when do you use 1 over lambda? When do you use the Rydberg equation? Literally never. I hate the Rydberg equation because the Rydberg equation only works for hydrogen, and it only works sometimes. My statement is to never use that equation. Alex will not ask you to do it. If you use it for a question like this and it's not an acceptable equation, I will take off points. You can always go through the way we're going to talk about in this equation to solve those types of questions. So please don't use the Rydberg equation. I hate the Rydberg equation because it gives you the false impression that you can use that to calculate that when it is more correct to go the other way, even if it gives you a similar answer. So you're required to do the calculation the correct way in this case. So it asks us to calculate the wavelength of light that is, talking about an emission here, from the n equals 6 to the n equals 2 state. So if you were to be asked to draw this transition, you would go starting at n equals 6, ending at n equals 2. And what is the wavelength of light? So let's start with the change in energy equals negative 2.18 times 10 to the negative 18 joules, 1 over nf squared minus 1 over ni squared. So let's plug that in, negative 2.18 times 10 to the negative 18 joules, 1 over 2 squared minus 1 over 6 squared. When you plug this in, you get negative 4.84. Let's make that bigger. Negative 4.84 times 10 to the negative 19 joules equals delta E of the delta E. Now, the change in energy is directly equal, but perhaps of opposite signs, as the energy of the photon. So delta E equals negative E photon because this is emission. And so we know that E photon is equal to h nu, which is also equal to h c over lambda. So I'm just manipulating equations here. In this case, so I took the E photon, which is in this case going to be equal to negative delta E. We would like to solve for the wavelength. So lambda equals hc over negative, negative delta E. So in this case, now we're just going to start plugging stuff in. 6.626 times 10 to the negative 34th joule seconds times 2.998 times 10 to the 8 meters per second divided by the wavelength of light, but the negative wavelength of light. So 4.84 times 10 to the negative 19 joules. When you plug this into your calculator, you get, it asks for it in, it does not ask for it in nanometers, but I will always ask for it in nanometers. So in 1 meter, there's 1 times 10 to the 9th nanometers, which will give you 410 nanometers. If by chance it doesn't ask for it in nanometers, I will accept it in meters, but it would in that case. So okay, so Jordan's asked about a bunch of other equations. So the de Broglie wavelength is for mass, which is definitely not a photon of light. So I derived that equation in the 6.2 video and showed you how to use it. So Jordan, let me ask you this question. In the video about the delta X, delta MV equation, did I tell you that we'll ever have to use it? So it looks like you're going down the equation sheet, and my recommendation would be to look at the equation sheet and look at the videos at the same time. You asked, is E photon always equal to negative delta E? Is that always true? No, because it matters whether it's emission or absorption. So delta E is equal to negative E photon when it is emission. Delta E is equal to E photon in the other case. So Kajal asks, isn't that 4.84 negative in the denominator? It is, but I erased the sign, but we could have left it as negative. I just think that that's messy, so what I did is, because this is negative delta E, I had eliminated that, but we can add that in for sure. So Catherine makes probably one of the most interesting statements. Not that everyone else hasn't said stuff. So she asks, or they ask, how do you know what kind of equation you're going to use? I can do math. I'm just confused about how do you know when to use what equation. So what I would do, there's two answers to this. The first answer is to write down what you know and ask yourself what you don't know. Because now this equation is like everything else all mushed together. So I would, and I tend to write up here on the right side, if you watch any of the videos, write down like, here's what I know, here's what I don't know, question mark, question mark. The other thing is, there's only a handful of ways that these questions can be asked. So my recommendation is to look for, okay, so this question, I like this question. I think the weekly assignment is very close to this, but a little different. So the more of these that you do, the easier it will be for you to do it on the exam. There will be a question just like this on the exam, including the drawing and everything else. Sarah gives you some really good points to talk about. Write down what you know and then look at the equation sheet. Because this is an open notes exam, I would even encourage you to write an equation sheet that you wrote, not mine, to look at yours and say, okay, here are the things that I know, here are the things that I don't know. When do I use this equation? Okay, in the video she said we're literally never going to use this, so you could cross it out so you don't get confused. But that's how that works. So other questions about questions 1 through 4, or we're going to kind of, I don't say change gears, but instead of thinking about math, we're going to start to look at electron configuration for the next 15 to 20 minutes left in our live session today. If you have any other topical questions about any of the videos, so Jordan, the answer to your question, so all of the ones you've asked about, most of them we're not going to use. The delta X, delta MV, that equation is virtually, it's not impossible. I show it to you because it's really important for why the quantum numbers are important, but we're not going to use the Heisenberg uncertainty principle? Yeah, the Heisenberg uncertainty principle. And the de Broglie wavelength, you will not be asked to recreate that calculation on the exam. All right, let's look at number 7. So we want to, in this case, it's going to ask you to write and draw, so both, the electron configuration for antimony, SB. So a lot of times students are like, well, what if I ask you to only write it or I ask you to only draw it on the exam? Which one is which? So let's talk about that. So if I ask you to write the electron configuration, writing is 1s, 2, 2s, 2, dot, 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 dot. Draw means to draw these arrow things. So in the videos I talk about why they need to only have one barb or no barbs or all the barbs in all the places. So in this case, I'm asking you to do both. You can always present both, but if I'm only asking for one and you give the other one, you will not receive full credit. So antimony, SB. I'm going to start by writing. Now, this would be a lot easier if I had a periodic table. You can use the periodic table and basically count as you go across. The periodic table tells you where the electrons are. So this is like when I think this class is super cool. The periodic table tells you where the electrons are, and it tells you how to fill this out. So we get, for the right, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, I'm going to run out of space soon, 4d10, 5p3. Now, neither of these say you can use the noble gas configuration. If you had the noble gas configuration, in this case, it would be krypton, which would remove some of these. So from here, we're going to draw this out. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. So this one is long. And now we're going to count to 51 as we put them in. If you watch the videos, I'm mostly going to apologize for the fact that you can hear me count them out. I count them out and follow Hund's rule every time. And that helps me make sure that I didn't add one, leave one behind, or anything else. So there are 51 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 32, 33, 34, 35, 36, 7, 38, 9, 40. 3, 4, 5, 6, 7, 48, 49, 50, 51. Ooh, lots of questions. So Genevieve asks, when should we use the noble gas configuration? I will tell you when you should if it is for a grade. It will say you can or you cannot, because I want to know if you can tell the difference. Aquatic Misery asks, on a right question, are we allowed to use the noble gas configuration if it doesn't say so? So it will tell you whether or not to use it on the exam. So just follow those directions. Jordan, that is correct. I will specifically say use it or don't. In this case, I don't want to say it's by default, but if you were going to do it, it would be krypton 5s 2 4d 10 5p3. So the noble gas configuration basically takes the noble gas from the row above, and then the rest of it fills in. So Ms. J asks, how do we know what electron configuration the element has left off of? Like if we wanted to use the noble gas and use krypton, how would we know where krypton left off as far as in 1s, p2s, et cetera, et cetera? That's a really great question. So this would work super well if I had a periodic table. Oh, I'm going to try something. I hope this doesn't. All right. I'd like to apologize for what's happening in your lives right now. So we bought these super fancy periodic tables on the wall, and I'm pretty excited to use it. So Ms. J also asks, how many marks does the F have, putting the electron marks? I'm going to come right back to that. So hopefully I'm so tiny, and this is not helpful, but it's the best we got today. So if this is antimony, it's the N equals 5 shell. Krypton is up one row, and it's element 36. So it accounts for 36 of the electrons. So when we think about that, you can basically say, okay, we're going to go up one row, and you can count across. So you could then say, where did the remaining, so if we used 36 of 51, I think that's the remaining 15 electrons. So that's how you can figure that out. Your other question was, how many marks does the F have? So the F orbital, how many, no, this is where this came from. So the number of M sub L's tells you how many pairs of electrons there are. So if L equals 3, we know that M sub L equals -3 all the way to 3 through 0, which is 7. So there are 7 F orbitals that contain 14 electrons. Now, how would you know that looking at the periodic table? Because the periodic table, I don't want to say is your best friend because that's weird and creepy, but we know that the F elements are these 2 rows down here, and so you can count across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There should only be 14. I don't know what that period is. The periodic table I provided for you only has 14. I think this one has a difference of where 2 of the electrons go, but there are only 14 electrons in the F orbital. Other questions? If you don't, we are going to do the same thing except for chromium. Also not using the noble gas configuration. So chromium is element 24. Well, that didn't work. That one was dead. Right out. So chromium has 24 electrons. So you would write, which we'll do that first. Um, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now, if you watch the video, you do know chromium is an exception. So we're going to look at that in just a second. So 1s, 2s, 2p, 3s, 3p, 4s, 1, 2, 3, 4, 5, 3d. So this answer here is incorrect. We're going to figure out why. So as we put in our electrons, following Hund's rule and everything, as we fill the d orbital, we realize that there are only 4 electrons in the d orbital. So these 4 electrons in the d orbital would actually prefer to be 6 degenerate orbitals where all have 1. So this here gets moved into one of the d orbitals to where you have 4s1, 5d5 in this case. So Jordan says the other one does too. I think it's because the d electrons in both of those rows only have 9. So overall, there are 10 electrons in both of those. And I believe the reason the lanthanide and actinide and I think beryllium and thallium, so 57, 58, 89, and 90 get a little different, that's why those don't necessarily follow the rules. But I will almost never ask you for the electron configuration of an f orbital element because they get kind of complicated. So what other questions do you guys have about chromium and why it doesn't follow the rules, right? So we always fill orbitals completely, and then we follow Hund's rule. So in this case, the 4s only has 1 electron. Questions, thoughts? Electron configuration is a pretty simple, in my opinion, process. There are some rules. We follow the rules. We like the rules. I don't want to say rules are our friends, but there are some rule breakers, and you want to make sure that you know who those are. So what other questions do you guys have? Thoughts, issues, concerns about the material from Chapter 6? Does anyone have any other questions about? So Ms. J asked, why doesn't this follow the rules? It's a good question. I like that question. So let's draw up what the non-rule following would be, or the rule following, 3D. So if chromium followed the rules, the 4s would have 2 electrons, and there would be 4 electrons in the d orbitals. And 1 orbital would be empty. So when I teach this in person, I like to talk about riding a bus. When I went to middle school, I rode a bus. When you get on the bus, most of us prefer to sit one to a seat, right? So half the route, there's one person to a seat, because then you have more space. Eventually, all of the seats are full, so you have to start pairing up. Electrons function almost identically to people on a bus. So the question is, why would these two sit together when there is an empty seat that's at roughly the same energy? So the 4s is always filled before the 3d in energy as we go up. But as the 3d gets more energy, these two become more in sync with one another, or more equivalent. So Hund's rule expands to encompass the 4s, basically with the half full or the almost half full d orbitals, as well as the almost full d orbitals. So if you look at the periodic table, the rule breakers tend to be in the same regions, because it is more energetically favorable to promote an electron out of the s into the d to get you 6 identically filled orbitals instead of 1 fully filled, 4 half filled, and an empty. So you also see this if you were to have the 3d only have 9 electrons, we will promote 1 out of the s to a fully filled d orbital. And in the 4d, it expands a little bit further because filling the 4d is more favorable than the 5s. So those they break the rules to make a more energetically favorable environment. Does that make sense? Any other questions today? If not, I will see you guys on Monday. I hope you guys have a good weekend. Happy studying for the exam. I think you guys will do great. Make sure you have notes. Make sure that you do the weekly assignment. And if you have any issues, send me an email. My office hours are on Friday, are from 10 to noon on Zoom. You can click the blue hyperlink that says Zoom on like the Canvas homepage for our course. Miss J, that's right. It really only happens in the d orbitals. Kajal, thanks for letting me know that you don't have any questions. I hope you guys have a fantastic week. I am going to go here in just a second. Y'all are great. Have a good rest of the day. Bye, guys. If you have questions, please come to office hours.